So this is Mat154 Pre-Calculus College Algebra 6.3. We're going to talk about simplifying radicals. Remember, we talked about radicals. Radical is the sign here, but we call it radicals because the index could be a square root or it could be a cube root or whatever. So we just kind of group them as radicals. So in this section, you're going to get a couple of things, a couple of handouts. One handout is going to be this one, which is a roots table. And this will give you the square root, and you read across to the left, or the cube root, you could read across to the left, the fourth roots, fifth roots, sixth roots, and so on. But make it a little bit easier. So if we had a cube root of 8, it would be 2. Or we can say if 2 was cubed, it would give us an 8. So here you have your radicands basically, and you're trying to find the root number that produced that. So I give you one of these and it might be helpful, especially with the cube roots, because 64 throws you off. Sometimes you're thinking it's a perfect square, but it's also a perfect cube. 4 times 4 times 4, 4 cubed. So there's a couple, these larger ones we don't use too often, but once in a while they come up. The other thing you're going to receive is what we call a breakdown chart. And we're going to be talking about that a little bit later. Also, I have your laws of exponents and conversions from radical form to, from rational form to radical form. So like 2/3, that would be, your index would be 3, the bottom number, top number is your power over index, power over index, power over index, power index. Okay, so we'll be talking about those, and we've got quite a bit of work to do, so let's get started. First thing we're going to do is practice multiplying radicals, which is pretty easy to do. If the indexes are the same, so both of these are square roots, all we got to do is multiply them together. You could write this step or kind of do it in your head. Square root of 3 times the square root of 5 is the square root of the quantity 3 times 5, which is the square root of 15. Okay, what if we had something like, this is on page 383. If you have a book, you can kind of just follow along. The square root of 5a times the square root of 2b. Well, that would be square root of 10ab. And that's pretty much it. Not much to it. Here's a cube root of 4 times the cube root of 5. And again, pretty easy. 4 times 5, 20. Still a cube root. Cube root times cube root, you can just multiply them. Even if it's in fractional form, something as strange as this, and this is all under this whole thing. I can do it very well. So this is a y. This is the fourth root of 7 times y, 7y, 5 times x, 5x. Just that simple. Okay, the problem is if the radicals do not have the same index, that's where we're going to take a look at one. This is example 5, 383. Here we have a situation where we have the square root of 5x times the fourth root of 3y. I do it pretty similar to the book, but I use just a slightly different way of doing it. Okay, let's first of all figure out what's the power and what's the index. On this one, the power is 1, the index is 2. On the other radical, the power is 1, the index is 4. I'm going to write them that way because I'm going to put them in rational form now. 5x to the 1/2 times 3y power over index 1/4. Okay, but we can't multiply, and I should put these in parentheses because it's the whole thing. There we go. So we can't really multiply these because they have different indexes. And remember, when you multiply like bases, we kind of add the exponents and weird stuff like that. So the little trick I use is, first of all, get the denominators to be the same. So let's change this from 1/2. We'll increase up that fraction. We'll multiply the top by 2 and the bottom by 2, and we'll write it as 2/4. Okay. Now, remember your denominator, this 4, is your index. So we're going to write this in radical form right away. This is a little different from the book. I'll put that in radical form. I'm going to cross these off. And now I have 5x to the second times 3y. They're all under the same radical, under the same roof. And now we can just calculate that out a little bit. Let's multiply this out. 25x squared 3y. So if we multiply that all out, we get 75x squared y. It does take quite a few little steps, but I like to put this step right, change them. So let's go over this just one more time. They were in radical form. We changed them to rational form. Common denominator, which is your index right here. So we could put them under the same radical. And then we just simplified that out, multiply these out and combine, So here we would just simplify. Simple math. Okay. So radical to rational, common denominator, common index, under the same house or the same roof. They all got to go together, and then we can simplify it. So let's try one more of those. I'm going to pick a problem here. This is on page 388. This is number 43. You have the 4th root of 3 times the square root of 2. Put a little dash there. Okay, so the 4th root of 3 would be 3. Power is 1. Index is 4. 2. Power is 1. Index invisible 2. Common denominator, fourths. 2/4. Okay, now we have a common index, which is 4. I like to cross it off. And now I have 3 to the 1, which is 3, and 2 squared, which is 4. So we have the 4th root of 12. Let's see if there's one more that's kind of wouldn't be too bad. Well, I just make it one. How about this one? This is 41. We have the square root of 2 times the cube root of 5. Radical form, 2 power index times 5 power index. So 2 times 3 is 6, right? So we're going to rename these with common denominators. So 3 times 2 is 6. 3 times 1 is 3. 3, 6. 5. 2 times 3 is 6. 2 times 1 is 2. Common index, 6. 2 to the third, 8. 5 to the second, 25. Calculator, or by using your brain, 8 times 25, 200. So we have the sixth root of 200. All right, so I hope that helps. Now we're going to start doing something called breakdown, breakout. Sometimes we have a large radical, like 50, and we want to break it down. So usually when we do this, we're going to break this down. We want to simplify it a little bit. And so we're going to divide it by a fairly small number, like 2. And that gives me 25. And we want one of these numbers to come out, my little thing here, as a perfect square. 4, 9, 16, 25, 36, 49, 64, one of those numbers. So 25, perfect square, 5 times 5. And what I usually do is I cross this off and I put it on top, meaning that it came out. Don't put it under a radical sign again. Okay, so my answer is going to be anything that's outside times what's inside, and that stays. So we say square root of 50 is 5 radical 2. Okay, so you're saying to yourself, what if you had 3 square root of 50? Okay, you do the same thing, break it down, break down the radical, 2 times 25, keep the 3. Just going to get rid of that. The 25 comes out as a 5. And now I'm going to multiply these two outside numbers. 5 times 3 is 15 radical 2. Pretty cool, huh? Okay. Now you're saying, well, what if I broke down 50 into 10 times 5? And my question would be, why would you do that? Because 10 is not a perfect square. 5 is not a perfect square. It's not going to help you. You need one of these numbers at least to be a perfect square. You know? So you can't, you want to use kind of common sense. Now, let's try another square root before we get into some of these really crazy ones. How about the square root of 18? Can you think of some numbers that give you 18? 6 times 3. Well, again, 6 and 3 aren't going to help you. They're not here. How about 9 times 2? And it doesn't matter what order you write them in. Say 9 is a perfect square. So the square root of 9, 3. I think of it as like they're locked up and they're trying to escape. Maybe they were in a prison camp and they're trying to escape from this prison camp. And the 3 gets out. I send for help. And he takes off. And radical 2 has to stay. 3 radical 2. How about square root of 20? 2 times 10, again, won't help you. 4 times 5. 2 radical 5. Okay, so when we look at something like, I would just do it right here, the square root of 8, we want to think of the square root of 8 as 2 radical 2. We want to think that in our head. We want to visualize that. Square root of 8 is 2 radical 2. Why? 2 times 4. 4 comes out as a 2. So rather than saying radical 8, if possible, we say 2 radical 2. We always try to reduce these large radicals down. Okay? Just by convention. The other thing I'm going to show you is a little trick. I'm going to show you on a fairly difficult problem. I'm going to take this number 11, 216x5, y3. And I'm going to do this a little different from the book. First of all, I'm going to break down to 216. So I'm going to take my calculator. I'm going to turn it on. 216, and I'm going to divide it by 2. It gives me 108, and 108 doesn't sound like a perfect square. Okay, I'm going to divide it by 3. Write this out. 216 divided by 3. Here we go. Oops. Okay, 72. Well, that's not a perfect square either. But I'm kind of thinking 72 could be 8 times 9, but it could be 2 times 36. So I'm going to break this down into, I'm just going to do the 216 maybe off to the side. And I'm thinking, okay, it could be 3 times 72. That's not going to help me. But 72 could be 2 times 36. 36 is a possible answer. And 2 times 3 is 6. So it's 6 times 36. So I'm going to break it down. Now, another thing I could do is keep dividing 216. I could divide it by 4. Now, 4 is a perfect square, but that's a pretty big number, 54. And 54 could be broken down. You could realize that. So let's go a little bit more. 216 divided by 6. I'm going to try to divide it by numbers that aren't perfect squares. Saying I got my 6 times 36. So one of these is not a perfect square. This is. All right. This one, a pretty difficult one to break down. And I'm going to give you a breakdown sheet. And what you might want to do is add a number like that onto the breakdown sheet. I don't have it here. These are perfect squares, but I don't have the 216. I could put it down here. Let me do it on another sheet of paper here. 216, I could write that as 6 times 36, which is 6 radical 6. See, this would come out as square root. So, may come up a couple of times, and now I don't have to think about it each time. These are some of them like 108, 36 times 3, not a very common one. You see, but that'll give me 6 radical 3. So I did some of the 96 again, 16 times 6. Here's your breakdown. So I'm going to give you that absolutely free today for just paying attention. Now, I'm going to write these other ones down. I'm doing this different from the book. I'm going to show you my technique. This is a square root, so it doesn't have an index written, but I'm going to write the index. First thing I'm going to do is simplify these numbers. 6, no, I'm going to circle it. 36, yes, it can come out as a 6. Now, what I'm going to do with these odd exponents here, I'm going to divide 2 into 5. 2 into 5 goes 2 times, and it has 1 left over. That means 2 went in here 2 times. It would be x squared with an x to the 1 left over. 2 and 1. These would be my powers. Okay, 2 goes into 3 1 time with 1 left over. So this would be y1. Y1 down here. Anything below the radical sign stays. Anything on top comes out. This is 6x squared y. Radical 6xy. And that to me is the easiest way to do it. You're just dividing. Remember, when you write this in rational form, it's power over index, means power divided by index. Power divided by index. It almost looks like a division, doesn't it? 2 into 3, 1 with 1 left over. Let's try another one of those, maybe something maybe not quite as complicated. Let's try this one. I'm just going to make up a problem. Okay, break down. Break out. That's the theory behind these. Break down, break out. Break it down. No, not 6 times 3, but 2 times 9. X3, just write these again. Don't worry about them. If there is no index, put a 2. 2 will stay. 9 comes out. I'm going to cross it off because it's out as a 3. 2 goes into 3 one time, 1 left over. 2 can't go in a power of 1. It's going to stay. 2 goes into 4 2 times exactly. That's okay. It's out of there. No remainder. So anything under the radical sign, anything above comes out, and anything below stays. 2, x, y. And now we broke it down. So if you just divide by your index into the power, a lot easier than what they're going to show you in the book. Okay, let's try another one. This is a cube root, and cube roots are always harder to work with. All right, so I'm going to pull out this sheet right here, the square root table. And I'm going to, actually more than square root, it should have said radical table. So I'm going to look down here. These are my perfect cubes. Okay, this number is a 16. There is no 16, so it's got to be numbers smaller than 16. We don't have to worry about any of these numbers, just numbers smaller than 16. So 8. Could I get an 8 out of there? Yeah, 2 times 8. 8 times 2. A7, B11. So what is 8 going to come out as? 8 is going to come out way over here to a 2. What is 2 going to come out as? There is no 2. It's going to stay. 3 into 7, 2 times. 2 times 3 is 6. 6 from 7 is 1. 3 into 11, 3 times. 2 left over. There we got it. So now let's write it down. 2a squared b cubed. But we want to make sure we write the index down. Cube root. I put that little index in there. Let's see, I forget about the 2 there. 2ab squared. These are the numbers that stay. See, so it doesn't have to be a lot of work. Okay, the last thing is kind of multiplying these together. Let's say you have the square root of 20 times the square root of 8. You could break them down first, and sometimes we do that, but sometimes we just multiply them and then do the breakdown. 160 sounds like a pretty big number, but we could probably break it down into 16 times 10, huh? So if it ends in 0, you can multiply it by 10 or 5 maybe. And 16 is a perfect square. And 10, well, think of what 10 could multiply. 2, not a perfect square. 5, not a perfect square. So it's going to be 4 radical 10. So you don't want to just leave it 160. You won't get full credit. You have to do the breakdown also. All right, here's another one. 3 cube root of 25 times 2 cube root 5. Okay, so we're going to multiply the outside numbers. They're going to be a whole number, 6. Then the radical, 5 times 25, 125. The cube root of 125, well, it's cube roots and bingo. 125 is a perfect cube, 5. So this whole thing comes out as a 5. So now we no longer have a cube root. We just have 6 times 5, 30. See, in the book they show a lot more steps, but we don't have to put all those steps in. It's really just as simple. As long as the indexes are the same, we can multiply them. Okay, let's look at another problem here. This is 15. This one looks pretty hard. Okay, let's multiply these together. 4 times 18, this would be a cube root. That'll be 72. Put them in order, x squared, y cubed. Okay, 72. Now look at this. There is no 72. It's going to be one of these numbers in here. Something times something is going to give me 72. So I'm thinking 72. 8 times 9 is 72. 8. 8's a perfect cube. I just put it down here. I'm running out of room. 8 times 9, x squared, y cubed. Time to come out and play. Sorry, you're a perfect square, but not a cube. 3 can't divide into 2. You're going to have to stay. 3 into 3 goes one time, evenly. So my answer is 2y. And remember, if there was something in front of here, I would multiply the 2y times it, not the index, but there was a number. And then this would be the cube root of 9x squared. And there's the simplified form. So it's a little challenging. You know. Dividing, well, what we do with dividing, and there's a little rule here. When you have two separate radicals, you can write them separately like this, or you could put them under one big radicand. We can write it either way. On dividing, there's three things we do. Number one, we try to divide it. Number two, if we can't divide it, we try to reduce it. Number three, if we can't divide or reduce, then we do something called rationalizing, which we're probably going to do more so in the next section. But we'll show you a little bit of it maybe in this section. So on my calculator, I'm going to divide 80 divided by 5. I'm going to move this out of here. And I get 16. So this is the square root of 16. And anytime you can simplify them, get rid of the radicals, you do. But don't put it back under the radical. I don't know how many millions of times I've seen that. The object is to get this 16 out. It has escaped. Yay! I'm out. I'm free. Okay. All right, let's try another one. Now, just like multiplication, they have to have the same indexes. They both have to be square roots or something like that. Okay, so we can divide radical by radical. You could put it under one big radical, or you could just kind of think I'm going to divide this radical by this radical because they have the same indexes, and that would be 5 cube root of 16, right? But 16 isn't a perfect cube. It's a nice perfect square. And you notice the number 8 comes up quite often. 8 will show up in 64. And the first ones come up quite a bit. So we're going to break this down into cube root of 8 times 2. This is a perfect cube. 8 comes out as a 2. And of course, we're going to multiply those. 2 times 5 is 10. Cube root, maybe it's easier to write the 3 first, of 2. 10 cube root of 2. You don't want to write these so big that you got something like this. I mean, it's like, 103 square root of 2. So you want to be kind of careful how you write the final answer. Be a little bit neat. Okay, we did pretty good on those two. Let's try another one. How about this one? 72xy over 2 radical 2. Well, I can divide the radicals, but this 2 is going to have to stay outside 2. 2 into 72 is 36. I can take the square root of 36, but my index is 2, and 2 won't go into ones. You don't usually write, unless you want to write it in rational form, but we usually just leave it. We want it in radical form. So the square root of 36 is 6, but that's all we're going to get. So we get 6 square root of xy over 2. Now we can simply divide the 2 into 6, 3 square root of xy. So I think they did theirs a little differently. And personally, I think it's kind of confusing. So this is the way I would do it. They did theirs in 1, 2, 3, 4, 5, 6, 7 steps. That's a lot of steps to do something simple. So we just wanted to divide the radical into the radical. Perfect square, took it out. Left what was there, and then we had 2 whole numbers. These are both whole numbers, so we could divide them. So sometimes the book doesn't always show you the easiest way. Okay, here's another one. The cube root of 27 over 125. Go to our magic chart here. Cube root of 27, 3. Perfect cube. Cube root of 125, 5. Perfect cube. 3/5. I don't know how many steps you can put in there. That's it. You could break them down into, separate little radicals if you wanted to. But I don't see the purpose of that. It's just more writing. Okay. Let's try one hard one. We'll try this 23. Let's try that problem. The cube root of a squared b4 over the square root of ab. Now, see, this one's hard because they have different indexes. So let's write this as let's see, maybe let's just go ahead and distribute this. This would be a to the 2/3, b to the 4/3, over a to the 1/2, b to the 1/2. So what we're going to do here is let's get the same number for all these radicals. Then we can put them all into the same house. So let's all change these to sixes. A to the 4/6. B, we're changing to 6. 2 times 3, 2 times 4, 8/6. Multiplying by 3, A 3/6. B 3/6. Now remember with powers you can subtract. So 4/6 take away 3/6 is 1/6. So that's going to stay on the top because the larger fraction is on the top. 8/6 take away 3/6 is 5/6. Now we can put them under the same index. It's both sixes, right? And this will be A to the 1, B to the 5. So that's how I would do it. I know they might have done it a little differently. Don't like to work with fractions too much. So we want to get out of the fractions as much as we can, but sometimes we have to work with fractions. So we have to put them in rational form. And then from rational form, go back to radical form. Okay. So there's some problems here in the book to try, see what you can do. I don't want to prolong this anymore. All right. Good luck to you.